Good morning. Please let me know if you can hear me. I hope y'all can hear me. Okay, good. Thank you, Kevin. I appreciate that. I'm going to give everybody just a few minutes to join on over here. This is the most frustrating technology situation, but what I'm going to do today is I'm going to talk about the last part of the packet, and then I'm going to go ahead and go back and rework and work through this long titration example that I skipped over before. So if after the new material is covered, I'll go ahead and ask an attendance question, and then y'all can populate it in the chat box. And then after that, you can stay and watch me work this titration. I can go over some answers on not some answers, but some examples from the packet. I did get a request for to make a video on like how to get started on the problems that are in the packet. Anyway, I did get an answer. So I did go through. That's why I was a little bit late getting into the session today, because I was finishing making up that video. I have no idea what's going on with the video, with Blackboard video, audio. It's a problem. But anyway, if you're currently on Blackboard and you can hear me, my video is not working. So video, jump over to my YouTube channel and join us. Here I am this morning. It's so exciting and wet and rainy, and I'm going to continue coming to the office as long as I'm allowed to, because I don't want to work at home. I can't focus at home. But anyway, I've also still got my phone, so the snippets, I'll be able to break down this long live feed until into smaller, more manageable chunks of information. So let's talk about, let me move my microphone. And so y'all have to give me some feedback on what you can see on this packet. Hopefully it will work out okay. All right. And it's so weird because on my screen it looks backwards, but apparently to y'all it looks okay. So is this an acceptable viewing for the most part? I know the angle's kind of weird. Let me try that. No, I don't like that. All right. Better. Okay, good. You can see it. It's not backwards. It's not upside down. None of that. Okay. If something happens, please let me know. All right, let me start my phone video here. Great. All right, so we are on page 16 of the packet. We're going to talk about precipitation. So what is precipitation? It is not raining. Well, it's raining outside, but that it is not referring to rain in weather. So precipitation is when you mix two ionic compounds that are in solution that results in the precipitation, and sometimes this is called crashing out. I'll give you some more demos of that in a little bit. I don't have an actual demonstration, but of one or more of the cross products. So you put two ionic compounds that by themselves are soluble, but some of the ions in solution, when they get together, they are not soluble, and that's a problem. So what happens is, they say crash out. I tend to say it makes snowflakes, because snowflakes are a type of precipitation, so that's how I kind of remember it. Maybe that works for you. But precipitation can be predicted. When we're doing precipitation reactions, we have to use the reaction quotient The reaction quotient, that is Q. If you don't remember what reaction quotient Q is, go back and find your chapter 15 notes and review it. I will go over this a little bit as well. So same kind of principle applies. Depending on how Q relates to K, which is what we did in chapter 15, only this time it's the solubility product constant K, which is a type of equilibrium constant, so that's not new information. So what happens is if Q is less, when Q is less than K, the solution is considered unsaturated. In an unsaturated solution, the reaction can go ahead and proceed in its normal direction, the way that we write it, to the right. I don't really care about right and left in this. What you need to know about this is it's unsaturated, and that means additional solid can dissolve. You can add more to your solution, and it's going to dissolve. When you get to the point where Q and K are equal to each other, then the solution is considered saturated. So if you add in additional solid to the solution, it does not, or it will not dissolve. What it does is, like, you can do this with a sodium chloride at home. You can just start adding salt after a point. It doesn't matter how long you stir it. It's just going to sit on the bottom. That is a saturated solution. Adding additional solid does not dissolve the solid. Then, if Q is greater than K, the reaction is going to go to the left because you have too many products. Too many products. So in this case, that means too many ions in solution, because here we're writing dissolution equations. So when we write our equations, we're going from solid. Here, let me write that out. So we're going to go from solid to the ions. So here we have too many products. That's too many ions. So excess ions are made. They become solids. And that's going to precipitate. So the excess solid there precipitates out of the solution. When you have a solution where you have too many ions and not enough solid, you can get to a point, if you heat it up and it does dissolve and then you start cooling it, at this point the solution is considered super saturated, and you're going to get solid that comes out. If you alter the temperature, that alters the K value. That's kind of a problem with, but we're not going to talk about that. But you can have a supersaturated solution. So remember the words: less than, equal to, greater than, unsaturated, saturated, supersaturated, and what happens? Can you dissolve more solid or not? That's the rundown there. All right, so here in our example, a solid solution that contains lead 2 nitrate is mixed with one that has sodium bromide. There's a solution that is 0.0150 molar lead 2 nitrate and 0.00350 molar NaBr. Does a precipitate form? All right. We're going to need some information here. First, we have to figure out what our possible products are. So the way that I do this is I write out the equation as a double replacement equation. So mix these, NaBr, back and forth. These are aqueous solutions, so we can say they're aqueous if you want to. So now let's have things that switch places. So sodium nitrate and lead PB, Br2. We're going to need 2 and 2. There we go. All right, so these are our possible products. So here you have to look or you kind of know, but this problem doesn't give it to you, but I'll give it to you on the test, don't worry. All nitrates are always soluble, no exceptions. So this is going to stay in solution. It remains aqueous. This lead 2 bromide is not necessarily soluble. So we're going to work this problem using lead 2 bromide. And if you look it up, lead 2 bromide has a solubility product of 4.67 times 10 to the minus 6. So what do we need to do? We need to write our dissolution equation. So PbBr2 dissolves into lead and 2 bromides. After you write your dissociation equation, you need to write your expression for K or Q. So we can say, since we're trying to figure it out, we'll say Q, but you could say K. It's just your equilibrium expression. So remember, we have to take into account the coefficients here. That's something we haven't had to do very much with acids and bases. But so there's 1 lead, and then the bromide, and we got to square that. So from here we have this. Now let's plug and chug our numbers from this equation. So Q equals concentration of lead. Lead nitrate, that's going to be this one. So 0.0150. And the bromide here, 0.00350. Those are small numbers. Plug those into your calculator. Make sure you can calculate this, 0.0150, 0.00350. So that gets, oh, nope, I didn't do it right. Squared. Got to put the square on there. I was like, that's not right. All right, so there's squared. Don't forget that. See, I told you I can make any mistake that's possible. 1.84, 10 to the minus 7. Okay, so now to determine does a precipitate form, we have to relate Q and K. So Q here, 1.84 times 10 to the minus 7. K is here. Which one is bigger? In this case, -6 is bigger than -7, so K is greater. If you're not sure what happens, go back up to the top of the page here. So when Q is less than K, the solution is unsaturated. Additional stuff can dissolve. So let's actually answer the question. The question asks, does a precipitate form? The answer is yes or no. In this case, the answer is no. We did all that work for a one-word answer. Wasn't that fun? Now, all right. We're going to talk about selective precipitation. We can use the fact that stuff precipitates out in order to design experiments to make sure the desired component precipitates out. So we can precipitate out exactly what we want. So we can do it selectively. We get to pick what we want, and we can use that. So when you have solubility rules, which I did not make you memorize, I gave them to you, so you don't have to worry about me jacking these up for you. Silver and bromide, according to the solubility rules, tend to be soluble, but they can actually precipitate out of solution if the concentrations are high enough. And that's what this is about. This section is about. Solubility is relative. All things are soluble to some degree. So there's kind of an arbitrary line about what's soluble and what's not. I'm trying to adjust the webcam. It is a bit of a problem. I've had this issue before. I'm going to try to get them to get me a webcam that zooms. Is that a little bit better? It's always better on my phone. But, all right, so what we're going to do is we can calculate the minimum required concentrations to precipitate things out. So how we do that, the minimum required concentration to get a precipitate is when Q equals the solubility product. So you have a saturated solution. So we're going to try to make a saturated solution because anything over this minimum is going to start getting us snowflakes. Now, we can also calculate the concentrations of the ions that happen to be remaining in the solution after we selectively precipitate. That makes things very fun. All right, qualitative analysis. I'm going to go over this very briefly. This is much more of a lab thing. If you're in lab, you're going to get to probably watch me do this on a video instead of getting to do it yourself. That will be fun. It's kind of sad that you don't get to do it, but qualitative analysis is one of my favorite things to do because there's no calculations. You just get to watch and make pretty colors. All right, so what we use qualitative analysis for is we use selective precipitation to determine unknown components in a solution. So what we do is we tend to run a qual scheme around stuff that we know will happen, and then we run an unknown, and whether what we expect to happen happens or not determines what we have. So difference between quantitative and qualitative. Quantitative actually depends on the amounts of ions that are present in solutions, which means you have to do calculations. So quantitative analysis is calculation based. That's what we're kind of used to doing in the lab. We're running titrations, we're making solutions, we're doing spectrophotometry. All of those do require math. Qualitative, on the other hand, only depends on the kind of ions that are present. Which ions are present? Are they there? Yes or no? That helps. Now, the good news is there are no calculations. What happens is if you add a reagent, so you're adding one reactant that's going to selectively precipitate one ion in the solution, but not any of the others. And so then you take your precipitate and then you separate it out and you just keep on going. So this is an example. This is not on the test. I'm not going to give you these. This will be in lab though. You have this mixture of all these different cations. And so first you add HCl. If you get a precipitate, it could be these or not. You move on to what's left in solution, adding hydrogen sulfide. If it precipitates out, it could be these. If it doesn't, you add hydroxide. If it precipitates out, if it doesn't, you're going to add ammonium biphosphate and ammonia. If it precipitates out, it's this. If it doesn't, it's one of these. And Again, it's just a matter of being able to follow a flow chart. Their picture in the book is in nice, lovely color. You don't have to worry about that. Just know what qualitative analysis is. All right. Last section, complex ion equilibrium. Going to cover this very, very briefly because you can get lost in the weeds on this real quick. When you have transition metals that are in solution, we talked about this with acid-base properties of salts a little bit, how iron and aluminum could act as acids. So this is based on that. Our transition metal ions, when we put them in solution, they are good Lewis acids. Remember, a Lewis acid is an electron acceptor. And so the water molecules will act as the Lewis base. So they are going to be electron donors. And what ends up happening is they form what are called hydrated ions. The ions are hydrated, so we're not actually making different stuff. They just all jumble together. That's called a complex ion because it's even more, can I move the paper down? Yes. That's more of it's more complicated than even a polyatomic ion. So this is like multiple polyatomic ions. So what you have is you have a central metal that is bound to one or more, I call these ligands. You can also call them ligands. That is appropriate pronunciation. What is a ligand? A ligand is a neutral molecule or potentially an ion that acts as a Lewis base to form some covalent bonds with the central metal ion. Example here would be silver. Silver ions get hydrated. You get silver and 2 waters, overall positive charge. When we do this in an equation, we just say it's silver plus 1. Now, if you have a stronger Lewis base than water, such as ammonia, NH3, NH3 is ammonia, it will actually displace the water and what ends up happening is, so instead of the silver being bound to the water, you end up with the silver, and that's a plus, being bound to the ammonia. Again, in solution, we're always going to write this as Ag+. I certainly am because I'm lazy. Now, this is on the homework. I don't anticipate putting it on the test. I don't think I did. But now, what's the deal with complex ions and solubility? Now, the solubility of an ionic compound that has a metal cation forms complex ions. Make sure that increase in the presence of our Lewis bases that are going to form a better complex ion. These are our Lewis bases that we're looking for that will do this are ammonia, the cyanide ion, and hydroxide. So these are our good Lewis bases. So if you add ammonia to the silver, it increases its equilibrium constant by a factor, if you care about this, 17 million. So it's way, way, way more soluble. So you can add these basic compounds to make things a lot more soluble. These are going to be metal hydroxides only. They all have the basic anion hydroxide. Obviously, they're called metal hydroxides. So, if you want to make them soluble, that means you want to make them break apart. How do you break apart something with a hydroxide on it? You add some hydrogen ions. So if it has an OH, it is definitely going to be soluble in acidic solution because this hydroxide is going to want to react with the free hydrogen to make water. So you're going to keep getting the equilibrium shifting to the right. It's a Le Chatelier's principle thing. As the OH is dissolving, you're creating products and then you're removing them because they're reacting with hydrogen. So you have to keep making these. So it's a lot more soluble. This is the only complex ion that I actually put as an example here. So you have aluminum hydroxide, and we're going to add some water, aluminum ion, and water. In this case, the aluminum hydroxide is acting as a base because it is accepting the hydroxide is accepting the proton to make water. So what that means is some can also act as acids in order to increase their solubility in basic solutions. Remember that anything, again, this is not on the test in any major form at all. It is on the homework though. Remember that, I forgot what I was going to say. Something that can act as an acid or a base is called amphoteric. It can act as an acid or a base. There it is, I said it. So here in this reaction, if you have aluminum hydroxide in a basic solution, you can get, it will accept the electron pair and give you this crazy complex anion. So if it's the electron pair acceptor, it's acting as an acid. So that's kind of weird. Now, it can act as an acid or a base. So that means it can be soluble in acidic or in basic solutions. But what happens if it's not acidic or basic? It's insoluble. It's insoluble at a neutral pH. So that just makes things really weird. Again, this is complex ions. They're complex for a reason, meaning they are very confusing. You get into a lot of the Lewis structures related to that. This is not going to be on the test in any major form at all. So that is the end of the new material. Let me think of an attendance question. Have I asked what your favorite ice cream is yet? I don't remember if I have. I know I was going to ask it, but type in the chat box, tell me what your favorite ice cream is. And then if you want to stay and watch me work out this very long example starting on page 10 for a titration, please do so. If not, you are free to leave. I'll also entertain some questions on the practice problems, but I did make you a help video separate for that if you want it to be. What was the last two blanks? The last two blanks were, It remains insoluble at a neutral pH. Get that under the webcam where you can see it. It is insoluble at a neutral pH. All right. So if you want to leave, leave. It is okay with me. If you want to watch me do some of these titrations, it'd probably be a good idea if you're not comfortable with the concept of titrations yet, doing all this math. So when you are ready, flip over to page 10. I'm going to grab some caffeine. Yes, I will be giving you credit for the amount that you do. It will be weighted. But if you don't, definitely turn in what you have. Always turn in. Some points is always better than no points. I will weight it accordingly. But to complete the entire assignment, to get the full 10 quiz points. It's a good question. Some people can decide whether it's worth it or not. All right. It appears that most of you want to continue on with me. Great. Let me get my calculation here. All right. Here we are. We have 20 milliliters of acetic acid. So acetic acid, that is a weak acid. We know it's an acid because we have a Ka value. I'll try to get this a little more focused, maybe. Let's try to bring this down a little bit. I don't know if that's any better, but I'm trying. All right, so we know that acetic acid is a weak acid, and we are going to titrate it with NaOH. That is a strong base. So we got to calculate 6 different things. The first thing it wants us to calculate is an initial pH. So before I get real started here, now I'm just going to go ahead and jump in. So our initial pH, that means when we have our initial pH, have we added any base? No. So we have no base has been added yet. So when you do your initial pH, when does it due? It says tomorrow at 11:59. I don't remember. It's end of day tomorrow. If I accidentally put AM, I meant PM. But remember that Blackboard is in Eastern time. So Eastern time would be 10:59. So be careful on that. So don't stay up too late. But I wanted to make sure you had a full day after I completed the material. Plus, I'll be here to answer questions during class tomorrow. I don't have any new material for class tomorrow, but I will be hopefully in the Blackboard classroom. We have no idea if this is going to even work, but if not, I'll be in my YouTube, and you can ask me questions, or we can find some sort of way to provide virtual assistance. All right, so we have our initial pH. We have not added any of our base, so this is just going to be a standard ice table calculation. So when we have, so let's write our acid dissociation equation. We know we have to do that because we have a Ka. If we had a strong base or a strong acid, it would just be equal to the molarity. So that's going to dissociate into hydrogen ions and acetate ions. If you prefer to put the water in there and make that H3O plus, go right ahead. I'm just lazy. All right, so here, ice table. Initial, we have 0.102, nothing and nothing. So we're going to make products, lose reactants, 0.102 minus x, x and x. All right, now let's use our Ka. So we know that 1.8 times 10 to the negative fifth equals x squared over 0.102 minus x. Okay, if we divide, can we use x as small? If we have m over k, is x small? Yes, it is, because 0.102 is definitely more than 2 orders of magnitude. If you want to see that on the calculator, go ahead. So x is small, mark it out. Here, I'll do it for you. 0.102 divided by 1.8, 10 to the negative fifth. Yes is bigger than 100. X is small. Fabulous. So 1.8, 10 to the negative 5 times 0.102. Let's take the square root. So we know that x equals 0.00135. So, and that is our concentration of H plus. So pH is going to be the negative log of that, 0.00135. I'm just going to keep going on my calculator and take the negative log of that answer. So our initial pH, 2.87. First part done. Next part. Volume at the equivalence point. Now, at the equivalence point, we know that our moles of our acid equal our moles of our base. So we can do this with stoichiometry. So I like to write out my equation at this point for what happens when I react my acid with my base, because I'm going to be needing that going forward. HC2H3O2 plus NaOH is going to make water and sodium acetate. If you haven't been with me or you forget that this is how I like to write water when I do these equations, it helps me to balance them. Let's check and make sure everything's balanced. 1 hydrogen, 1 hydrogen, 1 hydroxide, 1, 1. We're good. All right. So now let's take, we want to find, this is volume at the equivalence point. So that means volume of NaOH at the equivalence point. So let's start with what we know. 20 milliliters of our acetic acid. That's in the problem. And we know we have 0.102 moles of acetic acid per 1,000 milliliters. Next, stoichiometry. Use your equation. 1 mole of acetic acid requires 1 mole of NaOH in order to neutralize it. And now we need to know our volume. Where did I go? Did I get this upside down? Oh, no, I didn't. I need my molarity of NaOH. I know I have 0.125 moles of NaOH per 1,000 milliliters. All right. This is what we did back in Gen Chem 1. Y'all didn't like it then. Probably don't like it now. So 20 times 0.102. Here we can crash out those thousands. Divided by 0.125. So I got Make sure I get this. I got 16.32 milliliters. That's the answer. Next, this is asking, what is the pH after we have added 5 milliliters of NaOH? Now, here's when things start to get a little bit complicated, because we're going to have to do this using our millimoles, where we're adding, we have to do our stoichiometry, and then we have to do our equilibrium before we can get the pH. So we can look here, and we know how much it's going to take. There's a decimal here. How much it's going to take to get to equivalence. We've only added 5, so we're not at equivalence yet. So we've only added some. So let's write our equation here. C2H3O2 NaOH, going to make water, sodium acetate. Okay, now let's figure out how many millimoles we have of stuff. So starting out, we're going to have the same number of millimoles of our acetic acid in each one of these calculations. They are, so we have 20 milliliters times 0.102 molarity. So this is for our acetic acid. So here, 20 times 0.102, 2.04. 2.04 millimoles. So this is our before, then we're going to add, and then we're going to have our after. So before, we have 2.04 millimoles. Now, how much NaOH do we have? At this point, we have added 5 milliliters, and according to our problem, it's 0.125 molar. 5 times 0.125. 0.625. 0.625. So that goes on the add line, 0.625. Now, remember in a titration, the excess one is going to get used up, or is going to absorb it. So all of this sodium hydroxide is going to be used up. So this is going to be a minus 0.625. All that is used to neutralize this acid. All right. So, well, here we can say 625 if you want to. So if you prefer to write it that way, so we're going to subtract, because we want to have 0. It all gets used up. Now, over here on the products, we're also adding 0.625 millimoles. That's where, because this has salt properties, this salt has pH properties, so you have to be careful there. Now, so let's subtract here. So this is 0.625 when we add. After, how much acetic acid do we have? You can't see that. 2.04 minus 0.625. 1.415. 1.415 millimoles. All right. At this point, we have a buffer solution. If you're not sure, look at the ratio here. Is this ratio, if our ratio of acid to base is somewhere between 0.1 and 10, we can use the Henderson-Hasselbalch equation. If you're not sure about how to do that, if you don't remember, just do an ice table with your dissociation like you did up here. Then do it up here. But I like to do it this way. pH equals pKa plus the log base over acid. pH we're trying to figure out. pKa we need to take, we should probably just write that down. So we need negative log 1.8 times 10 to the negative 5. negative log 1.8 10 to the negative 5. If you don't know that the pKa of acetic acid is 4.74 yet, you haven't done enough of these problems. pKa of acetic acid, always 4.74. Plus the log. Be careful here. Remember what is your base and what is your acid. This is your acid. Here's your conjugate base. You got to be able to identify them and speak the language in order to do the math. So base, 0.625. This is a ratio. It doesn't have to be in molarity. 1.415. Figure it out. So plus the log of 0.625 divided by 1.415. So here, did I do that right? Yes. We have our pH equals 4.39 so far, because we have base over acid. Very good. All right, so now we have done 3 of our 6 questions. Next, part D. This says the pH at half equivalence. There's a shortcut here. At the half equivalence point, that is when pH equals pKa. So use the shortcut. pH equals, so you can say negative log, was it 1.8 times 10 to the negative 5 if you want to do that, or if you remember 4.74. Makes things better. Keep going. The next question said, what is the pH at equivalence? All right. So let's write our acid-base equation first. C2H3O2 plus NaOH is going to make water plus sodium C2H3O2, sodium acetate. Okay, so how much acid did we start with? So here we know again that acid equals base molarity-wise. So we had 2.04 millimoles of acetic acid to start with. So 2.04 millimoles. So how much? So this is at equivalence. So that means acid equals base. So that means we also have 2.04 millimoles of NaOH. So we're going to subtract that. You don't really have to show that. So that's gone. That's all neutralized. Here's what counts. We're adding 2.04 millimoles of sodium acetate. All right. What do we do with this? Well, we should write our dissociation equation, of course. So we got to write our equation for this salt. So if we have, the sodium doesn't matter. So C2H3O2, you can put it in there if you want to, but it's not going to matter. It's going to react with water. So this is your conjugate base. Water is going to be acting as the acid. This is your conjugate base, or in this case, it's going to be the base. And that's going to make acetic acid and hydroxide ion. That's what we got to figure out. Hydroxide ion. Okay. So let's take what we got. We got 2.04 we need to figure out our concentration here. So we have 2.04 millimoles. We need a volume here because we need a molarity. All right, so how much do we have? Over 20 plus, because that's how much we started with, 16.32 was how many milliliters of NaOH it was going to take. Plus 16.32. Let's figure that out. 20, oh, good heavens. 20 plus 16.32. All right. So 0.0562. That's what I'm going to go with. So 0.0562. Water doesn't matter. Here we're going to have 0 and 0, plus x, minus x. 0.0562 minus x, x and x. Now, when we do this equilibrium calculation, don't worry, we're almost done with this problem. This is a base. We're getting OH. So when we are doing this, we need to find Kb. The problem has given us Ka. So we know that Kb, remember that Kb times Ka equals K of water. So Kb times Ka, which was 1.8, 10 to the negative fifth, equals Kw, 1 times 10 to the negative 14th. You can't see that. All right, so let's see. What is Kb? 1, 10 to the negative 14th, divided by 1.8, 10 to the minus 5. Very small. Kb, 5.56, 10 to the negative 10th. Okay. So let's go over here where I have some room to write. Equals x squared. Again, this is our equilibrium. If you want to write the equilibrium expression before you plug and chug, go for it. Is x small here? Yes, x is definitely small. Leave it alone. So times 0.0562. And now let's take the square root of that. 5.59 times 10 to the negative 6th, if you can't read that, 10 to the negative 6th. And that equals our concentration of hydroxide ion. The question tells us we want the pH. So here we can, I choose to use a subtraction method. So I like to find POH and then subtract, or you could use KW and get concentration of H plus if you prefer. POH equals negative log of 5.59 times 10 to the minus 6. Again, since this test is going to be on the computer and you don't have to show your work, you don't have to write it all down if you don't want to. POH equals 5.25. So that means pH equals 14 minus 5.25. So what is 14 minus that answer? 8.75. 8.75. All that for one answer. Okay, now, last part. Thought, how in the world is she going to take up a page and a half? Yeah, these problems take a long time, a lot of space. It's easier to do it in the lab where you can watch it and do it graphically. But, all right, F. pH 5 milliliters beyond the equivalence. All right, what in the world does that mean? 5 milliliters of NaOH added after equivalence. So we need equivalence plus 5 mLs. So the equivalence was 16.32. So 16.32, 21.32 milliliters of NaOH. All right. So how many millimoles is that? Let's find out. Times, what was our concentration of NaOH? I forgot. 0.125. 0.125. 21.32 times 0.125. 2.665. 2.665 millimoles NaOH. Write your equation. Acetic acid plus NaOH makes water plus sodium acetate. You could use whatever shorthand notation you want. If you want to call this AA for acetic acid and like SH for sodium hydroxide, I don't really care. You can say acid conjugate base. It doesn't matter. You can use your notation however you want to do it. All right. Remember, the starting amount of acetic acid is always the same. So that was 2.0, you can't see that, 2.04 millimoles. So the 20 milliliters times its concentration. So that is still 2.04 millimoles. Now we have 2.665 millimoles of NaOH. Which one do we have more of? This one. So all the acetic acid is going to get used up. 2.04 millimoles. And just for consistency, put plus 2.04 millimoles of the acetate. I can tell you the acetate is not going to matter, but for consistency, you can put it in there. So we have 2.665 minus 2.04. So here we have 0.625 millimoles of NaOH. Remember now, and the reason in the first line, it says, yes, it is times 0.125. That's the concentration of the NaOH from the problem. So remember when I said when we have a mixture of strong versus weak acids or bases, the strong one dominates? We're going to use that same principle. So this is a strong base, this is a weak base, so this one doesn't matter. It's not going to be noticeably contributing to the pH value or the pOH. All right, so now in order, before we can calculate pHs and pOHs, we actually need a concentration. So we need to divide by the total volume, which was 20 milliliters of acid that we started with. That hasn't changed. 20 milliliters plus 16.32. Nope, that's not right. 21.32 milliliters of NaOH that we have now. So that is 41.32 divided by 41.32. So it's still small, 0.0151. 0.0151 molar hydroxide. Strong base, sodium doesn't matter. Next, we want to know the pH. So I'm going to find pOH, negative log 0.0151, negative log, whatever that answer is, 1.82. So pH, 14 minus 1.82. 14 minus that answer, 12.18. All that for a few pH answers. Wasn't that fun? All right. I am almost out of time for class, but if you have any specific questions right now for me regarding the practice problems, I can tell you that I did find a couple of typos and I've corrected them on the updated version that I have posted. In number 3, it's supposed to be acetic acid, and I had written nitric acid, so sorry about that. I took off the excess C that wasn't supposed to be there in number 8. And there was another one that I had. I thought I had another typo somewhere. I don't remember. But, so, class tomorrow, I will be at least starting out in the Blackboard classroom. We can jump over to YouTube if we need to. If you want to send me your questions ahead of time, I'm going to get my Getting Started on the Practice Problems video posted as soon as we're done. So you can watch through that, start working on them, work through them. If you have any questions, either about specific review material, questions on the practice problems, questions on the homework, let me know. I'll be able to help you work through them. Should be at the office in the office most of the afternoon, but I'll have access to email at home and stuff too. I do have a webcam at home, but it's not a mobile one like I have here. Oh, I guess you can probably see my face. Let's do that. Hi! There I am. I'm back. All right, so yeah, I may end up taking this webcam home in the event that campus closes, but we'll see. So thank you for being in class today. This is the hardest unit, in my opinion, that we do in all of Gen Chem as far as applications and things. Our next unit that we're going to do doesn't really go together at all. Chapter 18 is thermodynamics, which I hate. Most of you actually like. So we agree to disagree on that. Chapter 19 is electrochemistry, which I hate even more than thermodynamics. Most of you will probably love it. And then chapter 20 is nuclear chemistry, which is the easiest thing we will do all semester. What does 50% neutralization mean? That means half equivalence. So that's where you can use pH equals pKa. That's the shortcut. So half neutralization, half equivalence. It's a good question. Anybody else have questions right now? All right. Peace out. Feel free to leave. I'm here if you need me. Oh, thank you to everybody who sent me emails that you like my posters. I appreciate that. I just got them put up a couple weeks ago. So anyway, I'm going to end my live stream, but how like it will be out until August. I have no idea. That's something that, you know what, I just deal with information as I get it. So I don't plan for contingencies, really. I just wait until they tell me what's happening, and then I make a plan around that. So the situation is fluid. I will try to roll with the punches, as the case may be. If you're in lab, don't worry about anything in lab this week. After we get back from spring break, you're going to get to watch me do a bunch of labs or spend time in the lab, and I'll give you more instructions on that. So with that, I hope you have a fabulous day. Try not to get too soaked. Stay healthy. Nobody get fevers. Wash your hands. All that likely public service announcement information. All right. I will be in the classroom tomorrow. Hopefully I'll see you. If not, it won't count against you for attendance, I promise. All right. Video's coming soon. See y'all.